See that today I would like to discuss on that is force between two conductors carrying current. See here uh, we are considered two conductors, namely this we can call it X conductor, this is an Y conductor. These two conductors, how they are arranged? Parallel to each other. They are lying in the same plane. So XY are the two straight infinite long parallel conductors. You see, they are lying in a vertical plane. Perpendicular to it is that a cardboard is kept. Perpendicular to this XY plane, a cardboard is kept. So where P and Q are the 2 points. So just like you can say that this is my hand. For this hand you are inserting that say that any wire, is it? So like this here XY conductor. So they are looking like this only, is it? These two conductors are there. So in these two conductors we are passing the current. First conductor, in next conductor you are passing I1 ampere of current. In second conductor we are passing I2 ampere of current. So see, you are consider two conductors of infinite long straight parallel to each other. Such conductors you are passing the I1 and I2 amperes in the same direction. Is it? If it is the case, so what type of force will going to form between the two conductors? Whether the force of attraction will going to form between the conductors or force of repulsion will going to form between the two conductors. If the two conductors carrying current in the same direction, a force of attraction will going to form between the two conductors. So then question is that how the force, these two conductors will go to experiences the force. As you know that whenever a conductor carries a current which is placed inside the external magnetic field, that conductor experiences the mechanical force. Otherwise, you can say that interaction of the two magnetic field which produces the mechanical force between the two conductors. As a result, these two conductors will go to experiences the force. That is, in order to form the force between the two conductors, there is an interaction of the two magnetic field. As a result, these two conductors either repulsive force or attractive force. If the attractive force is there, these two conductors they will come very close to each other. If the repulsive force is there, so these two conductors are moving far away from each other. So in which case, in which conditions two conductors come to each other, I mean that two conductors will go to experiences the attractive force. So as I said it now, we are consider two straight parallel conductor of infinite length, infinite length. These two conductors are separated by a certain distance. You can say that A is the distance between the two conductors. So you can say that there is a small, say that 1 meter distance between the two conductors. These two conductors, they should be placed in the vacuum. These two conductors are placed in the vacuum and they should be perpendicular. They should be what? Parallel to each other. For this plane, you have to place a cardboard, is it? Which is perpendicular to the what? Plane of the conductor. So as you are already familiar that, say just for the sake of convenience, so you consider that only X conductor. In this X conductor you are passing the current I ampere of current. Whenever a conductor carries current or whenever you are passing current through any conductor, surrounding to the conductor a magnetic field is going to form. So this is known as the magnetic effect of electric current. Then question is that what type of pattern of magnetic field is going to form? Of course, whenever a conductor carries current, whenever you are passing current through any conductor, surrounding to the conductor a magnetic field is going to develop. Then what is the nature of the magnetic field? Whether it is a concentric circle or square, etc. So whenever a conductor carries current, this is so perpendicular to the plane of the conductor, over that concentric circular magnetic field is going to form. These are the concentric circular magnetic field lines are forming. So then question is that what is the direction of this magnetic field? How to find the direction of the magnetic field of magnetic field lines? So you see that this is the concentric circular magnetic field is that. So that in order to find the direction of magnetic field, so you have to use the right hand class rule. What it says that right hand class rule? So this is an X is a conductor. X is a conductor. In this conductor, current is moving in the upward direction. So this thumb, it should be, imagine that this is a conductor, X conductor. So this thumb, it should be pointed in the direction of current in the conductor. This thumb points this thumb in the direction of current in the conductor. The remaining fingers, which are encircling the conductor, which are surrounding the conductor, they are showing the direction of magnetic field. So that means that, here the situation is like this. So you see that current is flowing in the upward direction, thumb is pointing in the upward direction, remaining fingers, they are showing the direction of magnetic field. So like this, when this magnetic field, say, comes at the point, see that the magnetic field at this point is, the question is that what is the direction of magnetic field at Q point? So that means that another conductor, you are placed inside the magnetic field of X conductor. I mean that in the X conductor you are passing I ampere of current. As a result, surrounding to this conductor, a concentric circular magnetic field lines or magnetic field form. Is it? In that magnetic field, you have to place another conductor, say that Y conductor. The distance between the two conductors is, say, these two conductors are separated by a distance A meter. Is it? So that means that now second conductor, Y conductor, it is in the magnetic field of first conductor. I mean that X conductor. So as a result, what happened that these magnetic field, I mean that so at this point, what is the magnitude of magnetic field? So in order to find the magnetic field at this point, so you have to use that a straight infinitely long conductor carries current. The expression for the magnetic field at any point on the conductor is given by this expression, as you are already familiar with. So this is what the magnetic field at point P. See, magnetic field, magnitude of magnetic field, it varies from point to point. As you are going away from this X conductor, first conductor, magnitude of magnetic field, it will goes on changes. Is it? So now I would like to know that what is the magnitude of magnetic field at the Q point, which lies on the second conductor. Q point which lies on the second conductor, this point. So first step is that you have to find an expression for the magnitude of magnetic field at the point Q due to current passing through the first conductor. Is it? The first step is that, so explanation is that you are considered two straight parallel conductors. These two conductors are separated by distance 1 meter. So A represents the 1 meter. The direction of current either in the same direction or opposite direction. But in this case, direction of current is moving in the same direction. Is it? So now let us see perpendicular to the plane of the conductor. So you are consider this cardboard. So imagine that first you consider first conductor, S conductor. in the X conductor, say I1 ampere of current is flowing in the upward direction. As a result, over the cardboard, this cardboard is perpendicular to the plane of the conductor. Over this cardboard, concentric circular magnetic field lines are formed. So these are the concentric magnetic field lines are there. So in this magnetic field lines, so you insert another conductor, say Y conductor, in which I2 ampere of current is flowing. So if it is the case, so first step, because of current passing through the first conductor, that X conductor, at this point, how much magnetic field is going to produce? The magnitude of magnetic field at Q, step 1, magnitude of magnetic field at Q due to current flowing current I1 flowing in the X conductor. So I want to know that what is the magnitude of magnetic field at this point because of current passing through the first conductor. So that you can say that is nothing but the magnitude of magnetic field at Q, that this point. So it is due to the current passing in the X conductor, due to current I1 flowing in the X conductor, which is nothing but the, say, B1 is equal to mu naught upon 2 pi I1 upon A. So with this expression, we can say that this is an equation 1. So otherwise, you are already familiar that separate derivation that a state infinitely long conductor carries current. Very close to that conductor, if you consider a point. So a different point, what is the magnitude of magnetic field? So at different point, you can find the magnitude of magnetic field by using this expression. That a state conductor carrying current. The magnitude of magnetic field, suppose a state conductor carrying current, is it? So with this expression, otherwise Ampere circuit law also, you can find the magnitude of magnetic field at different points surrounding this this conductor. So now this is the word. So now what is the direction of magnetic field? So just we got the expression for the magnetic field. Now what is the direction of magnetic field? So what we have to do that? Just this is in a circle. It is a circle. Over the circle at this point, you have to draw a tangent. That tangent which gives the direction of magnetic field at this point. So that means that now in this case, the direction of magnetic field is inside the board. You see, which is perpendicular to the Y conductor, right? So now what happens that here you know that current, you know that magnetic field, this B1 is the magnetic field. So if it is the case over this conductor, that in the Y conductor, how much force will go to form? Because so a conductor carries current. In this conductor is placed external magnetic field. So if it is the case, this conductor, that second conductor, it is going to experience the force. So that means that a conductor carries current placed inside the magnetic field. You see, now two fields are going to interact each other. As a result, that second conductor is going to experience the force. Now the question is that where are the two magnetic fields? One magnetic field because of current flowing in the second conductor, I mean that Y conductor. As a result, a magnetic field lines will go to form surrounding this conductor. You see. Another is that because of current passing in the first conductor, a magnetic field is going to produce at this point. I mean that two magnetic fields, they are going to interact each other. As a result, this conductor will go to experience the force. So this type of force we are calling the mechanical force. So I think that you got a clear picture. Whenever a conductor carrying current which is placed inside the external magnetic field, now conductor will go to experience the force. Now the question is that what is the magnitude of that force? So if you know that magnitude of the force, that force it will go to act in which direction? Whether toward the X conductor or away from the conductor. Let us see here. So in order to find the direction of magnetic field, in order to find the direction of force which is acting at this point, which is acting on this conductor at this point, by using the Fleming left hand rule, we can find the direction of force on the second conductor. See, according to the Fleming left hand rule, what it says that stretched out first three fingers of the left hand. So this is the left hand. First three fingers of the left hand. I mean that you open. So how? They should be mutually perpendicular to each other. So first three fingers. This is the thumb, this is the forefinger, this is the central finger. So stretched out the first three fingers of the left hand so that they should be mutually perpendicular to each other. This finger is perpendicular to this finger is perpendicular to this. So and this finger is perpendicular to this. So that means that all three fingers they are perpendicular to each other. Now question is that this forefinger what it indicates? Forefinger shows the direction of magnetic field and single finger represents the direction of current in the conductor. So now third unknown is that this thumb gives the direction of force acting on the conductor. This is the situation is like this. You see that this is exactly like this. Now here this shows the central finger shows the what? Direction of current, whereas the forefinger shows the direction of what? Direction of magnetic field, and this thumb it gives the direction of force on the second conductor. That means that you see that the direction of force or this conductor can say that F2 it is acting towards the what? First conductor, X conductor. This force we can call that F2 is the force which is acting towards the what? First conductor. Now, as I said it, no, we got that because of current flowing in the second conductor and because of magnetic field forming at this point is B1. So, as a result, this second conductor is going to experience the force. Now, let us see. So what is the magnitude of force? How to find the force? How much force will going to act on the conductor? See, force acting on the second conductor, magnitude of force acting on the second conductor, magnitude of force. Step 2, magnitude of force acting on the Y conductor magnitude of force acting on the Y conductor due to current I2 in the due to current I2. So magnitude of force acting on the Y conductor due to current I2 is, So as you know that a state conductor carrying current, whenever a state conductor carries current, the force experiences the conductor that depends on the magnitude of magnetic field, it depends on the strength of electric current, it depends on the length of the conductor, it also depends on the what sine of theta. So that means that force on this conductor, if you want to know the magnitude of force on this conductor, the force on this conductor, it depends on four factors. First of all, it depends on the strength of current which is passing in the second conductor. Second thing is that at this point, what is the magnitude of magnetic field? B1 is the magnitude of magnetic field. And third point is that the length of this conductor. Fourth point is that the angle, sine of angle between this. So these four factors, the force experienced by the conductor depends. So that means that magnitude of force acting on the Y conductor due to current I2 is, so as you know it, that force, as I said, that F2 is equal to, so F2 is directly proportional to the magnitude of magnetic field. So magnitude of magnetic field is B1, is it? This second conductor which is placed inside the magnetic field B1, and it is directly proportional to the strength of current passing in the second conductor. That is, strength of current which is passing in the second conductor is I. The length, say L represents the length of the conductor. So apart from that, sine theta. So from this figure here, theta is 90 degree. So therefore, we can write it as F2 is maximum BI1 B1 I2 L into sine 90. So as you know that F2 is equal to B1 I2 L into 1 sine 90, because sine 90 is equal to 1. So now, so you can call that this is an equation 2. This you can call that equation 2. So you know that expression for B1 from equation 1. From equation 1, substitute B1 from equation 1. What is an equation 1? Equation 1, see, I will put it here. So F2 is equal to, in place of B, I will substitute that from equation 1, that is mu naught upon 2 pi into I1 upon A, that is I2 L, where L is the length. So this much force will going to acting on this conductor. The direction, in order to find the direction, as I said, that direction of this force is toward the conductor by using the Fleming left hand rule. By using Fleming left hand rule, direction of force which is acting on the second conductor toward the direction of force F2 is towards X conductor. So this, the direction of, in order to find the direction of force or the second conductor, you have to use the Fleming left hand rule. As I said, that Fleming left hand rule, what it said that, so stretched out the first three fingers of the left hand. So as you know that these are the first three fingers. See that this is the thumb, as you know it, this is the forefinger, this is the central finger. So this thumb shows the direction of force on the conductor, whereas this forefinger indicates the direction of magnetic field, central finger gives the direction of current in the conductor. So as I said it now, this is the situation quite like this. Say this, along the second conductor, this central finger represents the direction of current, where the forefinger represents the show the direction of current inside the rod, whereas the thumb gives the the direction of force on the second conductor, it is toward the first conductor. Now, same situation, similarly, you can evaluate the force which is acting on the first conductor because of current flowing in the second conductor. Say in the second conductor, current is flowing, is it? Force per unit length, you can find it, force per unit length, force per unit length, force, similarly, force on the magnitude of force F1, magnitude of force F1 due to current flowing in the second conductor. I mean that second conductor is nothing but the Y conductor. So what happens that you see that, so imagine that this is an Y conductor. This Y conductor, say that I2 ampere of current is flowing. So whenever a conductor carries current, so surrounding to this conductor, a circular magnetic field lines will go up to form similar to this. So now in this case, what happened that this type of circular magnetic field lines will go up to form. So now you are forming the circular magnetic field surrounding to the second conductor. Now the question is that, now the first conductor, it is inside the magnetic field of second conductor. So in the second conductor you are passing I2 ampere of current. As a result, surrounding to this conductor, a magnetic field is going to develop. So in this magnetic field, first conductor is placed, is it, at this point. Say that conductor, say at P point, what is the direction of magnetic field? So you know that just you have to, this circular magnetic field lines, so you have to draw a tangent, so that gives the direction of magnetic field. So this is the direction of magnetic field, it is toward the observer. I mean that perpendicular to the plane, but it is toward the observer. So you know that two things, one is that magnetic field, that is B2, and you know that current which is passing, strength of current which is passing in the first conductor. If these two things you know that, if these two parameters you know it, then you can find in which direction this conductor will go to experience force, whether toward the Y conductor or away from the Y conductor. In order to find the exact direction of the what force which is acting on the first conductor, once again you have to use the Fleming left hand rule. According to Fleming left hand rule, what it said that, so once again, stretched out first three fingers of the left hand side. So these are the first three fingers. As you know that this central finger, what it gives? Central finger, what? Say this looks like this. Central finger represents the direction of current in the X conductor, whereas this forefinger gives the direction of current in the direction of magnetic field over the conductor, and this thumb, it shows the direction of current, direction of force over the X conductor. So in this direction, the magnitude of in this direction, force will go back. This force I will go to call that F1. So once again, as I said that, so this is the situation like this. So this is the situation. You see that central finger, it overlaps with the direction of current in the conductor, whereas this forefinger, it represents the direction of magnetic field. But this thumb, it gives the direction of force on the first conductor. So that means that the direction of force of X conductor is towards the Y conductor. That means that whenever two conductors of infinite length if you pass the current in the same direction, the force will go to form between the two conductors. These two force, that is an attractive force, will go to form between the two conductors. That's why these two force, direction of these two forces are, that they are coming to closer to each other. So that means that the attractive force will go to form between the two conductors. One conclusion we drawn from this figure, this theory, whenever the two conductors of infinite length separated by 1 meter apart, between the conductor, a force of attraction will go to form. That is F1 and F2, they are coming very close to each other. That means that the attractive force will go to act between the two conductors. So now let us see. So according to this, you see that F1 is equal to, similarly got an expression for the F1 is equal to mu naught upon 2 pi into I2 A I1 I1. So you see that these two forces are equal in magnitude, opposing in directions. So therefore now let us see what we have to do. That force per unit length, force per unit length, force per unit length, force per unit length. So that is, you can say that F1 is equal to F2, which is equal to F, because magnitude of first force, which is equal to magnitude of second force. Say that forces are equal, you can say that F is nothing but the force. That force per unit length, force per unit length, which is equal to, you can write it in the expression for the force per unit length, that is F is equal to mu naught upon 2 pi into I1 I2 into L. This L get cancelled. Finally, we will get an expression for this, that is F is equal to mu naught upon 2 pi I1 I2 upon A Newton per meter. Newton per meter. So this is the expression for the force between two conductors carrying current in the same direction. Now the question is that when these two forces are acting in the when the two conductors carrying current in the opposite direction, what is the nature of